washing machine at home, it goes back and forth, and so forth. Along the respiratory tract, you suck air in, and you blow it back out, the same way it came in, and so forth, so it's in and out, in and out. But that's not the way the blood circulates. The blood circulates like this, one direction only. And what keeps the blood going in one direction only are the one-way valves in the cardiovascular system. And we have 4 one-way valves right here within the heart itself. For example, right here at the origin of the arteries that conduct blood away from the heart are one-way valves called the semilunar valves, because, well, to the anatomists that named them, they look like little moons. The semilunar valve at the origin of the pulmonary trunk is called the pulmonary semilunar valve. The semilunar valve at the origin of the aorta is the aortic semilunar valve. Okay? When the ventricles contract, these valves open to allow blood into the arteries, and when the ventricles are relaxing, the valves close to prevent the blood from backing into the ventricles. Now, between the atria and the ventricles, we also have one-way valves. These are referred to as the AV valves. AV, that's not audio-visual, no, that's atrioventricular valves. The valves between the atria and the ventricles. And, well, they're probably more famous valves than the semilunar valves. Certainly easier to locate if you're dissecting the heart. These valves open to allow blood to move from the atria to the ventricles. And then they close to prevent the blood from moving back into the atria when the ventricles contract. So when the ventricles contract, the only place for the blood to go is into the arteries, past the semilunar valves. The AV valve on the right side of the heart is also known as the tricuspid valve, whereas the valve on the left side of the heart is known either as the bicuspid valve, because it has 2 cusps instead of 3, or it's also known as the mitral valve, named after the bishop's mitre hat. That's not the one you're wearing, the bishop's mitre hat. Well, think of it in these terms. RI on the right, tricuspid valve. Notice these valves have a special structure. They have attached to them little cord-like structures called tendons that anchor the valve to the wall of the ventricle via these projections from the wall called papillae, or capillary muscle. Little extensions, muscular extensions from the wall of the ventricles that these thread-like structures called the chordae tendineae attach to. And what these structures do, the chordae tendineae with their associated papillary muscle, is to prevent these valves from prolapsing, that is, from opening up backwards. They're a special support system for these valves. Especially important on the left side of the heart, where you generate such high pressures. In fact, if you have valve failure, it's most likely to occur on the left side, not the right side, because the left side generates so much higher pressure than generated on the right side. Why do you suppose that's so?
Push blood through the body.
It's got to push blood a much longer distance from that. So if somebody has a defective valve, it's probably a defective aortic valve or a defective mitral valve. These little threads, the chordae tendineae, are your heartstrings. When somebody's tugging on your heartstrings, for example, that's what they're tugging on, your chordae tendineae. Say, oh, leave my chordae tendineae alone. Up, down, up, down, up, down, up, down, up, down. What you're hearing are the heart sounds, which are primarily the sounds of the closing of the 2 sets of valves. When the ventricles contract, notice that the AV valves close, and you hear the lub sound. When the ventricles relax and fill, the semilunar valves close, and you hear the dub sound. So the two heart sounds you hear are the closing of the two sets of valves. Lub, dub, lub, dub, lub, dub. When the ventricles contract, we call that systole. Systole is from a Greek word meaning contraction. The AV valves are forced closed, so that the only way the blood can leave the heart is to exit via the arteries, the aorta and the pulmonary pump. When the ventricles relax and fill, we say the heart is in diastole. That means between contractions. And that's when the semilunar valves close, so that the blood doesn't back into the ventricles. The blood that we just ejected from the ventricles doesn't back into the ventricles. We want the blood to move in one direction. So the heart sounds typically are lub-dub, lub-dub. Sometimes you may hear lub-slush-dub, and that's the sound of a leaky valve, for example. A valve that isn't closing properly and is allowing blood to move in the wrong direction, which may not be a problem, unless maybe you're exercising, which is a problem then, but it may become a more serious problem and require surgery. And since the 1960s, they've been able to do open heart surgery, open up the chest, and actually go inside the heart and even replace the valves in the heart. Sometimes they use the valves from pig hearts, for example. They've also used artificial valves, like snorkels. I knew a fellow who had an artificial valve in his heart, and if you sat near him, you could hear it clicking away. Click, 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 click. Weird. I would hate to have that, you know. What if it didn't click? That's bad news. Did I write my will, you know? I mean, it's like the ticking of a clock. You know, it's the clock always ticking. From people who they feel their heart pounding in their chest, that's usually uncomfortable. They don't like that feeling. But think if you had to listen to your heart click, click, click all the time, it would be artificial. Well, the muscle in the wall of the heart is primarily cardiac muscle, a special type of muscle, different in many ways from skeletal muscle that we studied earlier. Here again is a view of skeletal muscle. Skeletal muscle cells, or fibers, as we call them, are multinucleated. You can see in this picture, 3 nuclei visible there. Several different cells here. Skeletal muscle cells are striated. They're striped, in other words. And each cell has to be told by a nerve cell to generate an action potential and to contract. Now here's cardiac muscle. Cardiac muscle is similar to skeletal muscle in that it is also striated. There are striations in there. So it's striated muscle. Striated muscle. But the cells are a single nucleus. They have a single nucleus. They don't require neural innervation in order for them to contract, but they do require an action potential. But in cardiac muscle, the heart generates its own action potential for the muscle cells to contract. So the heart doesn't actually need the nervous system to continue to contract. And once you generate an action potential, say in the right atrium of the heart, the muscle cells of the heart will conduct the action potential to each other.